Welcome to The Explainer. Today, we're tackling a massive, literally astronomical challenge and a pretty revolutionary solution in the world of astrophysics. You see, the upcoming Nancy Grace Roman Space Telescope is absolutely going to change our view of the cosmos. But there's a catch. Its data scale is so staggeringly vast that it's fundamentally breaking how we do science. We are standing right on the edge of a big data frontier, and today we're going to look at exactly how researchers are completely rebuilding astronomical infrastructure to fix it. So let's just dive right in with a very practical question. How exactly do you download the entire universe? Or I guess more specifically, what happens when our space telescopes become so incredibly powerful that their data actually breaks our traditional computers? Because this is a very real physical problem we're facing right now as we gear up for Roman's launch. We're not just talking about a sluggish laptop here. We're talking about data sets so large they would literally melt down a standard hard drive before a fraction of the transfer was even complete. To really grasp the sheer ambition of this mission, we have to think about the technological leap we're taking. The Roman Space Telescope has the exact same pristine, awe-inspiring resolution as the legendary Hubble Space Telescope. But it is equipped with a wide-field instrument that gives it a field of view 100 times larger than Hubble. 100 times. In the past, astronomers had to painstakingly stitch together hundreds of tiny individual images over months just to see a fraction of a galaxy like Andromeda. Well, Roman captures that enormous swath in a single magnificent snapshot, completely eclipsing the footprints of both Hubble and Webb in one go. Now, when you scale up the field of view by that much without losing resolution, the pixel count absolutely explodes. Roman boasts a 302 megapixel camera. That means a single Roman image file is a massive 8 gigabytes. Think about that for a second. 8 gigabytes is the size of an entire computer operating system, and Roman is packing that into just one single photograph. That vastly dwarfs the file sizes from our previous flagship missions. For context, Hubble images are a mere 13 megabytes, and even Webb sits at around 2 gigabytes. Section 1. The Big Data Bottleneck. When the traditional data model breaks. Capturing a massive 8 gigabyte image is an incredible feat on its own, right? But doing it continuously creates a tidal wave of information. Because of its expansive view and rapid survey speed, which, by the way, surveys the sky up to 1,000 times faster than Hubble, Roman will downlink roughly 11 terabits of compressed data every single day. That translates to nearly 1,400 gigabytes of data relentlessly raining down from space every 24 hours. A 1,400 gigabyte download is a massive, hours-long chore for a high-speed fiber home network. But continuously receiving and processing that stream from a satellite in deep space, that requires an incredibly robust pipeline. And the thing is, that relentless stream literally never stops. When you stretch that daily deluge out over Roman's 5-year primary mission, it accumulates to an unfathomable 20 petabytes of data. 20 petabytes? The sheer scale of this ever-expanding archive is completely unprecedented for a space telescope. Sure, space agencies have dealt with large datasets before, but they have never had to manage an ocean of cosmic information that grows this rapidly and continuously. To put that into an everyday cosmic perspective, trying to download that 20 petabyte archive to your local university server, or worse, your own laptop, would be like trying to store 10 million high-definition movies all at once. You would run out of hard drive space in a fraction of a second. If you tried to do it on standard home Wi-Fi, the download time alone would literally take centuries. So yeah, the old way of doing astronomy, downloading files to your local machine to study them, is officially dead. It is physically and financially impossible. Which brings us to Section 2, the paradigm shift, bringing compute to data. Because of this massive bottleneck, a totally new core philosophy was born. If downloading the files is impossible, then instead of moving the universe to the scientist's computer, we move the scientist's computer into the cloud, right alongside the universe. By shifting the analysis to cloud-based servers where these massive datasets already live, we completely eliminate file transfer times. We're talking about saving scientists months of idle waiting. Plus, we entirely bypass the need for researchers to buy expensive, superpowered local hardware just to open a single file. This structural solution is called the Roman Research Nexus. It's a powerful, cloud-based science platform built directly on Amazon Web Services. The entire 20 petabyte data archive sits securely in the AWS cloud, and the Nexus provides the computing environment co-located right next to it. Why does that co-location matter? Well, when your computing power is sitting in the exact same server farm as your 20 petabyte archive, your data transfer latency drops to basically zero. You're interacting with the universe instantly. Section 3. Inside the Research Nexus, the Open Cloud Frontier. So what does a typical day actually look like for an astronomer using this system once operations begin in 2027? It's beautifully streamlined into just a few simple steps. First, an astronomer logs in with a standard MyStart account, which is essentially NASA's authentication system. From there, they open a pre-configured Jupyter notebook. That's an interactive web-based coding environment right in their web browser. Now, if they need more power to process, say a massive star catalog, they simply scale up their CPU and memory resources with a click, and boom, they begin analyzing data immediately. They're essentially spinning up supercomputer power right from a basic laptop on their couch. Furthermore, the Nexus comes preloaded with an entire suite of open-source tools. You get your standard Python libraries, plus mission-specific software like RomanCal for image calibration and Pangaea, the exposure time calculator. You even get persistent storage across your sessions. Historically, a graduate student might spend their first 3 months on a new project trapped in dependency hell, just trying to install software and get their local environment to run. The Nexus eliminates that friction entirely. It's ready right out of the box, accelerating human discovery by removing all that tedious setup. And finally, Section 4, an open access universe, democratizing the cosmos. Now, the technology of the Nexus is only half the story. The other half is a monumental cultural shift in astrophysics. Unlike a lot of previous space missions, there is absolutely no proprietary waiting period for Roman's data. Historically, the scientific team that proposed an observation might get 6 months or even a year to look at the data exclusively, carefully guarding it before anyone else could see it. The stakes were incredibly high, but not with Roman. The moment the data is beamed down and processed, it is public, zero exclusive access. By combining completely open data with scalable cloud computing, the Roman Research Nexus completely shatters the hardware and financial barriers that used to keep smaller institutions out of the loop. You no longer need a massive grant to buy a supercomputer to participate in cutting-edge astrophysics. A passionate astronomy student at an underfunded community college now has the exact same immediate access to the 20-petabyte Roman archive and the exact same computing power as a tenured professor at Harvard. This is true democratization of science. Independent researchers and global collaborators can all access and analyze the freshest datasets simultaneously. It really boils down to this. Anyone with a login can now explore the edge of the universe from a web browser. It truly brings an everyday cosmic perspective right to our fingertips. It opens the stars up to the entire global community, completely leveling the playing field and inviting everyone to participate in the scientific process. We've gone from a single 8-gigabyte image that would choke a traditional hard drive to a brilliant paradigm shift, bringing the compute directly to the data, culminating in a completely open, democratized universe. With the computational heavy lifting handled entirely by the cloud, and with a 20-petabyte ocean of cosmic data instantly accessible to anyone, anywhere. What mysteries will you be the first to uncover? Thank you for joining me on this explainer, and keep looking up.